Okay, so how is everyone today? Good, I hope? All right. So last time we were talking about parametric equations, and we've got a lot more to say about those. Okay. So to summarize where we were last time. So today's what, the 10-10? Hey, it is, isn't it? 10-10. So last time we were considering this. So we had x is equal to t squared minus 2t, and we had y is equal to t plus 1. And we made a nice table of values. And then after we made that nice table of values, then we plotted them. I had a tape malfunction. I'm having another tape malfunction. And when we did that, we got the following results. So if I call those big tick marks 2, then we had a point at 8, negative 1. So 8, negative 1. So that'd be 2, 4, 6, 8, and then negative 1. And we had another point at 3, 0. So that'd be 3, 0. We had another one at 0, 1. Really? So 0, 1. There. Then we had a point at negative 1, 2. Okay, and if you recall, it was a parabola. So now from here, I can just by symmetry do it. So there, there, there. Okay, so we plotted those points. And the thing I wanted, among the things that was stressed is that that's just some of the points there. But this was the point that was at t is negative 2, and then that was the one that was at t is negative 1, and then t is 0, 1, 2, 3, 4, going around. So what I want to convey is that I hope that you have some sense that we're drawing that way, from this way that way. So, signifying the direction of drawing with those little crow's feet, with those arrows. Okay. Good. Then the next thing we talked also about an ellipse. So that's in your notes. So I'll leave that there. And then the place where we stopped for a moment was at conic sections. So now we're going to have just a brief review of conic sections. So, in some sense, the easiest one is a circle. So the circle centered at the origin has this formula. So x squared plus y squared is r squared, and of course this is a circle with radius r greater than 0. Okay. So that would be the circle of radius r centered at the origin. And if we wanted it centered somewhere else, say at the point hk, then the equation becomes x minus h, square that, plus y minus k, square that, is r squared. So that'd be the circle centered at HK. Now, one thing that's not very common to do, but I'm going to do it just for sake of illustration, is that if I take the circle, the equation for the circle of radius r centered at the origin, and I divide both sides by r squared, then I could write it like this. I could say that this is x squared over r squared plus y squared over r squared is 1. You know, that's kind of a weird thing, but it is true nevertheless. Similarly, I could take this one and say that this is x minus h squared over r squared plus y minus k squared over r squared is equal to 1. Okay. Now, the reason for me to do that is that if you take a circle and then you know, squish it a little bit, and you do it, you know, just right, or smear it out, if you want to think of it that way, then what's the name of that conic section? An ellipse, right? So now, to have an ellipse, the way you do it is you take this strange-looking way to write the circle equation. So blah 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 equal 1, and what you do is you change the radii so that now this one will be some value squared, and this will be other value squared. So an ellipse is like this: x squared over a squared plus y squared over b squared is 1. So in this case, now we have that a is some positive number and b is some other positive number. So to get to the equation of ellipse, you take this sort of strange-looking equation for a circle, and then more or less change the radii to be two possibly different numbers. Now, when those are the same number, well, that's that, isn't it? Okay. Similarly, we could do the same thing to this one. X minus h squared over a squared plus y minus k squared over b squared is 1. So, you know, this one would be an ellipse centered at the origin with x radius a and y radius b. And this would be an ellipse centered at HK with x radius a and y radius b. So notably, the relative size of a and b tells you whether or not it's squished like that kind of an ellipse, you know, like that kind, or like that kind, the tall kind or the short kind. So, meaning to say that if a is less than b, that means that its variation in the b direction is, or in the y direction, is more than in the x direction. So it would look like this. So it would be tall. And if it's the other way around, a more than b, it would be like this. Okay, and then these are just the same, except now instead of being centered at the origin, they're centered at HK. Notably, this equation and that equation, these two, don't tell you, like if you wanted to take, say, this ellipse right here, you could say, oh, it's just right, except I want to grab it and I want to rotate it by like pi over 6. You know, so that it's not straight up and down like that, but just rotated, you know, like that. But we're not really going to discuss that much in the class. So in the end, to get ellipses that are rotated a little bit, what you would need is, instead of just having x's by themselves and y's by themselves, you'd also need xy's. You need some kind of x times y thing, but we're not going to deal with it. Okay, that being the case. So considering the previous example, this, x equal t squared minus 2t, and y is t plus 1, when we made a table and then plotted the points on an xy plot like this, we noticed it looks like a parabola. It looks like a parabola. Now I want to algebraically justify to you that, yeah, it really should look like a parabola. So for example, here's the way to state the request. I want you to, well, this t, the variable t, is called the parameter. And what we want to do in this exercise is we want to find an equation which eliminates the parameter. Okay, now this one is pretty straightforward because now concerning these two possibilities, x is that expression in parameter t and y is that other expression in parameter t. Concerning these two, which one does it appear to you would be easier to solve for t?
Y.
That one, right? So in principle, you could do it for that one. You could solve for t, but you know, there'd be in fact two different possibilities because you'd have to use the quadratic formula and things like that. So this one is this one's pretty straightforward. So what I want you to observe is that we could take this if I copy them down, oops. And say x is wow, I'm having writing problems today. Minus 2t. If I refer to that one as equation 1 and refer to this one as equation 2, so equation 1 just in parentheses, and this one as equation 2. So from 2, we can obtain that t is y minus 1. Right? And now we can put that into equation 1, which is to say everywhere in equation 1 where I see a t, I'm going to replace with y minus 1. So now it looks like this. X is y minus 1 squared minus 2 multiplied by y minus 1. And now I'm going to collect like terms and get x is, well, that'd be y squared minus 2y plus 1. So that's foiling that bit out. And then this would be subtract 2y, add 2. Okay, so then collecting, we have x is y squared, and then minus 4y, and then add 3. So now, what this is this is a parabola, right? Because it says x is this quadratic in y. So x is that quadratic in y. You know, if you, in your mind, substitute x's and y's, then it might look more comfortable to you, but you need to, you know, get accustomed to seeing whatever variable is equal to whatever. So does this quadratic factor? How does it factor?
Y minus 1, y minus 2.
Very good. So you could write it like this. So x is y minus 1 multiplied by y minus 3. So what this is this is a parabola. It's a parabola, and because it's x equal to y, and because we always draw the y-axis vertical and the x-axis horizontal, that means that this parabola opens to the left or to the right, not up or down. Furthermore, does it open to, so which one is it? Does it open left or right? I mean, we know because we drew the picture, right? But why does it open to the right? Right, because the leading coefficient is positive, which means it has to open into the positive direction instead of into the negative direction. Okay, furthermore, because of these factors, you can see that, when y is 1, there should be an intercept. And when y is 3, there should be an intercept. So what I'm saying is that from this alone, you can deduce that, well, it's got to be a parabola that opens that way. There must be an intercept at 1 and 3, so like there and there. And then, okay, it's got to go like this. More or less. And you can see from this page, oh yeah, that is more or less correct. But what I want you to observe is that when you eliminate the parameter, when you get to here, notice that this equation tells you in some sense what it should look like, but it doesn't tell you how it was drawn. Okay? In particular, what this is saying, what these two equations together are saying is it's saying that, well, if you were to start at -2, then you'd start drawing like this, and you'd draw it like that. So to signify that that's what we were doing, we put those little arrows to say that, you know, that's how we were doing it. But this one has no notion of, you know, were you drawing it like this, or were you drawing it the other way? So the distinction here is that this pair of equations tells you how it's drawn. That's what the parameter is encoding for you, how you're doing it. This one right here has no parameter, so it's not telling you how it's drawn. It's just telling you what's supposed to be there. Yes?
Is that what you meant by eliminating the parameter?
Yeah. The parameter is eliminated. Notice that this equation has no t in it. So it's gone. All right. Now, last time, we did an interesting one. Or did we? I can't remember. So last time we had something that had sines and cosines. So does anyone have their notes readily available? It was cosine of something and sine of other something. 2 cosine. 2 cosine t, and then y was what? Sine t. Yeah. So then, and we said this much. So 0 less or equal t less or equal 3 pi over 2. And then, you know, we carefully considered that problem. We made a table, plotted a bunch of points, and we came to the conclusion that, more or less, that when you draw it, it ends up looking like this. So it kind of looked like an ellipse. So we plotted a bunch of points, and they, you know, ended up looking like that, just that much, just 3/4 of an ellipse. And we said that, you know, when we plotted the points, we noticed that the drawing is happening in this direction. Okay, so now we want to justify that. So it looks like an ellipse. Now I want to convince you that it doesn't just look like one, it is one. So why? So for this exercise, now let's eliminate the parameter. But this requires some cleverness. Now, concerning the two possibilities, x and y, what I want you to see is that, in fact, neither one of them is particularly convenient for the purposes of solving for t. Right? So like for this one, you know, you could say t is arc sine of y. But that's fraught with difficulty because remember that this is little sine. But little sine is not invertible, only big sine is invertible. Right? Remember we talked about cutting the branches of sine and saying, oh, well, this is the invertible part. And this is little cosine, it's not big cosine. So switching to arc sine and arc cosine is fraught with peril. We need a different way to go. So specifically, what I want you to remember is I want you to recall the Pythagorean identity. That the cosine of any theta squared plus the sine of any theta squared is what?
1.
Is 1. And what I want you to observe is that, okay, for example, for the x equation, it's not particularly easy to solve for t. But can you solve for cosine of t? Yeah, that's easy, right? And then in the y equation, it's not particularly easy to solve for t, but can you solve for sine of t? Yeah, that's already done, isn't it? So note that we can say that the sine of t is y. That's easy enough. All right. And then I can also say that what? Cosine of t over 2 is x. Is that right? No. I have that backwards. Rather, I want cosine of t is x over 2. Now, I can plug those into the Pythagorean identity, which is to say, this one can go there, and that one can go there. So therefore, what we have is x over 2 square that plus y square that is 1. And then with a minor modification, I can say that this is x squared over 2 squared plus y squared. And then for reasons that I hope are clear, I'm going to write y squared divided by 1 squared is equal to 1. So what is this? This is an ellipse, right? This is an ellipse. What is the x radius? 2. So it's whatever that number is. So that's why you got to write it in that standard form. So it's that number, 2. And what is the y radius? 1. That's exactly what that is. Now, so this is an ellipse centered at the origin. With x radius 2, y radius 1. Now, this equation by itself if you were to just plot it, it will look like this. So that is that one. So in particular, I want you to notice comparing this one down here to that one up there. Notice that the one up here doesn't include all of the ellipse. Why not? Yeah, because the boundaries on the parameter. The parameter was only between 0 and 3 pi over 2. So when you eliminate the parameter, you also, in some sense, eliminate your access to that knowledge, right? So now you don't know. Okay. Furthermore, this equation for an ellipse, it doesn't tell you how the pen moves when you draw it, which is to say that did I draw it in going like counterclockwise? Did I draw it going clockwise? Did I draw it really quick? Did I draw it slowly? all of that information is lost. So why is all that information lost? Because we got rid of the parameter. That's what the parameter is saying. It's saying how the pin moves. Okay, so eliminating the parameter gives you a very good idea of like the overall structure of what it is that you're looking at. You could say, oh, I eliminated the parameter, and because I'm familiar with conic sections, I know that oh, it's got to be an ellipse, but it's probably just part of an ellipse. It's probably not all of it. And furthermore, this is not telling me, am I going clockwise or counterclockwise, or what am I doing? Okay. Any question about this? So now let's do an entertaining one, slightly entertaining, and then we'll go to the next thing. So for example, I could say, how about x is equal to -3 plus 4 cosine of t, and y is 2, and then, I don't know, plus 7 sine of t. Okay, so please eliminate the parameter. And furthermore, I'll say that just for interest, that its pi is less or equal to t is less or equal to 3 pi over 2. So what are you supposed to do? In fact, you need to take the same strategy as the previous exercise. So in the previous exercise, we solved for sine, and we solved for cosine. And then we used the Pythagorean identity. Okay, so in the interest of time, for the instruction, eliminate the parameter. Concerning the x equation, we can solve for cosine and say that cosine of t, well, if we wanted to solve for cosine t, we'd need to move that -3 over and then divide by the 4. So we'd have x plus 3 over 4. And then concerning solving for sine, we'd want to move the 2 over and then divide by the 7. So we've got cosine solved for, we've got sine solved for. Now we can use the Pythagorean identity and conclude that this x plus 3 over 4, square that, which is to say cosine squared, plus y minus 2 over 7, square that, which is to say sine squared, must be 1. Then, you know, just a little bit of algebraic work gets us to something like the following. X plus 3, square that, divide by 4 squared, plus y minus 2, square that, divide by 7 squared, is 1. So now what is this? So this is an ellipse. It is centered at -3, 2. Its x radius is what? 4. And its y radius is 7. Okay. Neat. So a quick sketch of just this would be, so I'm not going to try and draw like tick marks and make it real accurate, but at least I want to make sure that I have the center in the correct quadrant, right? So in which quadrant is it? Quadrant 2, right? Top left. So that means left side, that means top side. So the center, you know, is like maybe like right there. So that's the center. And then in the x direction, we need to go 4 to the right and 4 to the left. So maybe maybe like that and that. And then the y radius, we need to go 7 up and down. So you know, maybe that much and that much, something like that. And then this red is the actual ellipse. Okay, so you can kind of see it there. And then now, in such questions, it's you know, they, besides eliminating the parameter, they also want you to actually plot this. So now you could plot a sequence of points, plot a table of points, and say, okay, well, maybe I'll evaluate at pi and 7 pi over 6 and what have you. Okay, so evaluate carefully. So when you plot this, what that means is that you're going to end up plotting part of this ellipse. All the points that you must plot when you plot the parametric equations, they must fall on the ellipse. And when you do plot that, you will observe the following. So if this point is there, and there, and there, and there, and there, then the underlying ellipse looks like this. But the only points that actually exist, because we're plotting from pi to 3 pi over 2, in fact, you'll get that point, and you know, depending on how many points you plot, it will end up looking like that. So you just get those, and then you would get this much, and then you'd have to consider, oh, you know, in what order was I plotting those points? And the answer, you know, you'll need to watch carefully, but you're going in the counterclockwise direction, so like this. Okay. So eliminating the parameter and being familiar with conic sections tells you, in some sense, like, oh, this is like the skeleton. Okay, and then carefully plotting says, and in fact, we're just getting this part. Okay, good. Any question about this? But you know, this is neat and everything, but in some sense, it's kind of boring because this is a calculus class, right? We haven't talked about limits and derivatives yet. So here it comes, right? So now we want to do the calculus of this stuff. So this is section next section, 10.2. The calculus of these things. And really, the whole shebang can be summarized with this one statement. In some sense, you know, I can just write one thing and then be done with it. And that is that you know, in these equations, there's 3 symbols. Now, most of the calculus that we've done with so far, there's been just 2, like x and y. So you could say, like, you know, y is exponential of x. So there's y's and x's. But now we have 3 symbols. We have x's and y's, and we also have t's. So there's a 3rd symbol at play. Now, what I want to remind you of is that, you know, we talked about the Lotka-Volterra predator-prey model. And in that case, we also had 3 symbols, right? We had R's and W's, which stood for rabbits and wolves. But the number of rabbits and wolves was changing in time, so we had even a 3rd variable, and that was t, right? So in that case, we had 3 variables, R, W, and t. And it came to pass, when we wanted to sort of understand how the number of rabbits and wolves evolves over time, you know, how their populations change, we made a slope field that just included rabbits and wolves, and we eliminated time. Do you remember that? So we eliminated the t so that we were looking at dw dr. Okay. How did we eliminate the parameter t? How did we do that? We used two important calculus theorems. What are they? The inverse function theorem and the chain rule, right? And the chain rule. So, which is to say that, the chain rule the chain rule is saying something like this, that if you have a function that tells you how to turn, say, t's into x's. Okay? So, you've got a rule, like x is some function of t. And then you've got another rule that's telling you how to change x's into y's. So you know how to make an x from some t's, and you know how to make some y's from some x's. Then that means that combining those together, you should know how to make some y's from some t's, right? But you've got this intermediate step. You take these t's, turn them into x's, and then you take those x's and turn them into y's. Well, that's composition, and the way that the derivative interacts with composition is called the chain rule. Okay? Which is to say that if you have something that looks like this, y is a function of x, and you also have that x is a function of t, then you can differentiate f with respect to x, but you could also differentiate f with respect to t. So dy dt would be, according to the chain rule, well, you first differentiate f with respect to x, so you get dy dx. But now you have to include how this action included changing the t's into x's. So what does the chain rule say? You must multiply by dx dt. And using this Leibniz notation, that is to say the dy over dx and things like that, it's kind of cute because even though these things aren't fractions, if you suspend that knowledge for just a moment and say, well, I'm going to imagine that they're fractions for a moment, and you were to make some cancellations, what would cancel on the right-hand side? The dx's, and you would have dy over dt. Okay, so the chain rule is saying that. And also, the inverse function theorem, well, it's saying that if you have a function f and it has an inverse. So the last time I did this, y'all seemed to not like it. So I'm going to make it clear for you. Which one do I want? F inverse. Yeah. So if we do this, if we have a function f and its inverse, and we plug in an x, and then we take that result and plug it into the inverse, then what comes out? Just x, right? So if what your function does is multiplies by 2, then the inverse divides by 2, right? To undo that. So if you take a 5 and you multiply it by 2, and then after you've done that, you divide by 2, what do you have? A 5. If you take an x and you compute the exponential, and then after you do that, you compute the logarithm of that, what do you have? X, right? So that's true. Now if we differentiate both sides, then what's the derivative of the right-hand side? So I'm going to differentiate both sides. Whoops. So what's that? 1. And then to do this, because that's the composition of two functions, inverse and original function, that means according to the chain rule, we'd have the f inverse, calculate its derivative, evaluate it at f of x, and then multiply by f's derivative evaluated at x. So what that's telling you is that you can solve for this one in terms of that one. So you can say f inverse's derivative evaluated at f of x is equal to 1 over the derivative of this. And sometimes it's written in the other way where you solve for that one, but what have you. So when you convert this to the Leibniz notation, it becomes sort of too cute for words. So what I want you to notice is that we have the derivative of the inverse is evaluated there at f of x. But the derivative of the function is evaluated at a different place. It's evaluated at x. So notice that these are evaluated at two different places. But when you change this up, this becomes statements like the following: that dy dx is equal to 1 over dx dy in the Leibniz notation. So that's what it's saying, and that's the reason why I say it's kind of too cute for words, is that that's not a fraction. That's not what it is. But if you suspend that knowledge for a moment and say, well, what if it really was a fraction? Then we're doing 1 over that fraction, right? And then, well, instead of dividing by that fraction, I could multiply by its reciprocal. And what's the reciprocal of dx over dy? dy over dx. But that's cute, but you've got to be careful to remember that that's a function, and that's a function, and that one is evaluated at one place, and that one is evaluated at a different place. But, okay, fine. So what that's telling you, as a consequence of all of this, is therefore, if you have parametric equations, x is f of t, and y is g of t. So you've got parametric equations. Then you could eliminate the parameter, maybe, if the problem is easy enough, and you can figure out how to do it, either with trig or what have you. Then you could calculate it. Once you did that, you could calculate in principle dy dx. But in fact, you don't have to eliminate the parameter to calculate dy dx, because, have a look. Do you see that formula? dy dx is in that formula, according to the chain rule. Okay, and then we have also these things according to the inverse function theorem. So have a look at that one. Can you solve for dy dx? Yeah. We could say that, therefore, dy dx is equal to just dy dt over dx dt. All right. So let's have some examples of using this. So notice that again, that's almost just like too cute for words. That's not a fraction, but if we were to treat it as a fraction, instead of dividing by that fraction, we'd multiply by the reciprocal, and what would cancel? The dt's, right? Okay. That's why the Leibniz rule is useful, because it sort of uses that trick. But you have to be careful to remember that those things are not fractions, they're actually functions. Okay. So for example, we could say that x is t squared, and y is t cubed minus 3t. Now, for this particular set of parametric equations, it's not easy to eliminate the parameter. So in particular, you could do it, but you'd have two different equations. The reason is because this is a cubic, and that's a quadratic, And concerning these two, if you wanted to solve for t, which one would be easier? That one, right? But in fact, you'd have two different solutions. The reason is because when you compute square root of both sides, then this, the square root of t squared, is what? Not t. Absolute value of t. And so now it splits into two parts. In the same kind of way that concerning a circle, you can't solve for y. You could solve for the top half, or you could solve for the bottom half, but you can't solve for both halves at the same time. You have to have two different equations. So eliminating the parameter is a little bit complicated. In fact, if you were to plot this carefully and plot a whole bunch of points, then you'd see kind of a beautiful picture that looks like this. So at this point, so that's the origin, and here we have this point 3, 0. If you were to plot lots and lots of points, then it would look like this. So it keeps going in both directions. Now, what I just plotted there, is that the plot of a function? It's not, right? It's not the plot of a function, y is a function of x, because it doesn't pass the vertical line test. So that, by virtue of that, that's the difficulty that you would face in trying to eliminate the parameter. Essentially, you're fighting the fact that you can't really solve for y and just have one equation. Okay, nevertheless, the way I drew it, I didn't really say exactly how I drew it, right? Did I, in some sense, start down here and then draw that way? Or did I start up here and draw the other way? Right? I didn't really, it's not clear what I did. But do you observe that right there at that point, there's two tangent lines? There's the tangent line that we would obtain when we're, sort of ignoring that part, ignoring those parts. There's a tangent line sort of going that way. And ignoring this other part, there's a tangent line going the other way. Okay, so let's find the slopes of those tangent lines. So we want to find the slopes of those two tangent lines. Okay, so that means that we want to evaluate dy dx at two different times. Okay, so in the first place, let's find dy dx. Okay, well, as we wrote on the previous page, according to the chain rule, we need to find the derivatives of each one of these with respect to t. So dx dt would be what? 2t. And dy dt. Very good. Minus 3. Okay, and as a result, dy dx is what? Well, it'll be that one, right? Divide by that one.
Yeah.
So it's dy dt over 2t. notice I want you to see something that's a little bit curious, is that we're saying that dy dx, the rate at which y changes with respect to x, is this expression that's entirely in terms of t. Right? That's a little curious, isn't it? Under previous circumstances, this was usually something with x in it. Okay, so we want to evaluate dy dx at two different values of t, and now we need to figure out, well, at what times did that occur? So what are the t values? So how can we do that?
Put that in terms of t, x in terms of t.
Well, let me ask it like this. According to the picture, so I said that that point is 3, 0. So what's the x value there? 3. And what's the
0.
What's the y value? 0, right? So what we want to do is we want to solve. X equal to 3, y equal to 0 for t. Okay. So then substituting in x, that would be t squared is 3, and also t cubed minus 3t is 0. We want to solve that for t. So, well, the first equation is pretty straightforward. It's sort of just telling you what the solution is. What is it? Or negative square root of 3, right? There's got to be 2. Why is there got to be 2? Because there's 2 different tangent lines, right? So the fact that there's 2 tangent lines means there should be 2 solutions. All right. So, according to this, according to equation 1, from 1, we know that t should be negative square root of 3, or t is square root of 3. And if you carefully do this one, you'll from this one you get from equation 2 you get 3 possibilities. Oops, you get 3 possibilities. T is 0 or negative square root of 3 or positive square root of 3, because we hit the axis 3 times. 1, 2, 3. So finally, I know we're out of time. We can answer the question. So dy dx evaluated at the first time. T is negative square root 3. So this notation is called the evaluation bar. That means take this and plug in negative square root of 3. So what do you get? Well, that'd be 3 times 3 is 9 minus 3 is 6. So that'd be 6 over 2 times the square root of, times negative square root of 3. So then you get what? Negative 3 over square root of 3? So what is that telling you?
Negative square root of 3.
Well, yes, but that's telling you that the slope of that is negative 3 over square root 3. And I leave it to you to verify that the other one is going to be the negation of that. Okay, good. Have a nice Wednesday.